So I really want to start with a very serious thank you to the committees, so many committees that were involved, because it was not a triviality to get this tribute to Ian Macdonald in place and to make it happen. And a lot of people, I think, worked very hard to make that happen. And the whole community came together for Macdonald, which I think is a great thing for our community, given what Macdonald has done for us. So Macdonald is my hero, absolutely, in mathematics, and it is a great, it touches me very deeply to be asked to give this lecture. So I want, again, it's my favorite community, and to give such a lecture to this community really is special for me. So I want to start then with SFB, which, given that we're now here in Germany, in the German academic community, you know what SFB stands for. This is Sonderforschungsbereiche, right? Which means collaborative research grants funded by the DFG. But not for this lecture, no. SFB means Symmetric Functions Bible. Okay. And this is the Bible, as we all know. I started on this Bible when I was a graduate student. I was taking a course from Adriano Garcia, and we were all told to buy the Bible and to read the Bible and to live by the Bible. And it has absolutely, for me personally, been the right thing. It has made my life really wonderful all around. So I want to start. So I've chosen a few pieces of mathematics which I find extremely beautiful from Macdonald. And I think of them like works of art, like going to the museum and seeing them. Macdonald's oeuvre was huge, actually, and I'm going to try to give a little bit of a part of that. So the ones I hope, in fact, I hope that your favorites are not the ones that I have chosen from Macdonald. That I have chosen a few that are special, I think, to the community at large, but I hope that you have also your part of Macdonald's work that has touched you or will touch you. So Macdonald's polynomials I find very, very beautiful. These two formulas for the Schur function were more or less what kept me in mathematics all these years. I find these completely amazing formulas. So, and what's even more amazing is the fact that they're equal. So the real theorem on this slide is the fact that the left formula is equal to the right formula. So the first formula is a generating function for semi-standard Young tableau. So this is a tableau of size 665511. So that means that this row has 665551. And semi-standard tableau means, of course, that these are strictly increasing and these are weakly increasing. And then you just take the we're in combinatorics world. We do everything by generating functions, and so we should do it by generating functions. And so this tableau here has a weight, right? This tableau that we're looking at has a weight, which is x1 to the number of ones which appear, 1, 2, 3, and x2 to the number of twos which appear, 1, 2, 3, 4, 5, and so on. So this is x to the t. And you take this generating function. Okay, so that's our first favorite formula for the Schur function. And now we go to the other one. So this is the bideterminantal formula. So this A is defined by this sum over the symmetric group, signed sum. So it's a determinant because it's a signed sum over the symmetric group. And x to the mu is just taking a monomial. And so even though I have written it in terms of an action of the symmetric group, so I want to focus on that for a moment, an action of the symmetric group on polynomials. And I'm taking alternate, we were doing invariance in the last 2 talks ago, and so these are the alternating, the sign isotypic component of the polynomial ring. Or we could just say it the way Jacobi did, and say that there are 2 determinants, you need to divide one by the other. And of course, this bottom determinant is very special. This is the Vandermonde. And I like to tell my students that no matter what kind of mathematics you do in life, you will need to learn the Vandermonde. It will hit you. And so it's impossible not to discover this Vandermonde. Okay, so, and then that's the big theorem, is that in fact these 2 expressions are equal. And even today, when I think about how do I prove that? How do I know that the generating function of semi-standard Young tableau is a quotient of 2 determinants? Or think of it the other way. Take a quotient of 2 determinants and expand it. And how do you find it? It's just completely amazing. Okay, so now what did Macdonald do? So these are Macdonald polynomials. So this P lambda is a Macdonald polynomial. And Macdonald says there is a formula for the Macdonald polynomial as a sum over semi-standard tableau. And there is a formula for the Macdonald polynomial as a quotient of 2 determinants. They're not really determinants anymore, but who would think it, right? That the Schur function, you should have been looking at I have been working with a composer the last couple of months, and the composer is in the conservatory, and she asked me, you know, so you're going to Germany to give a lecture about Macdonald polynomials. What did he do? And I was trying to think, what do I tell this composer? And then I said, well, you know, it's like the computer here. And then the computer, you do something and it projects the slides and everybody thinks that's wonderful. And Macdonald comes and he puts 2 knobs here. One is called Q and one is called T. And these are 2 parameters. And you can move the parameters and the pictures just become more and more and more beautiful. Right? So this, who would have thought you could take the Schur function and put 2 knobs to get, you know, new sounds and everything. So this is what he did. All right, so I want to explain those 2 knobs. So Macdonald's setup is such that when I take this formula and I specialize Q and T to 0, it becomes this old formula for the Schur function. And when I take this formula for the these are no longer bideterminate, and I specialize Qt to 0, it becomes this determinantal formula. So everything is working in complete analogy. Except, I'll say it now, I'll go ahead and say it now, except the proof. Macdonald proved this, but Macdonald's proof goes through an inner product and a double affine Hecke algebra action. I don't know how to prove, I don't know how to make the Schur function proofs have the knobs, right? So this is really very much open in my mind, anyway. Okay, so let me explain a little bit about this action. So we said that this action here is a symmetric group. And this action here is the Hecke algebra. All right, so the symmetric group changes to the Hecke algebra. And these monomials here, so these are just monomials. And these E mu's, well, it says here, these are the electronic Macdonald polynomials. So this is a fundamental thing about Macdonald polynomial theory, which it took me too many years to realize. But symmetric group turns into Hecke algebra. Monomials turn into electronic Macdonald polynomials. Electronic Macdonald polynomials is the name that we coined. So I gave a bunch of lectures in Melbourne about Macdonald polynomials, and we were fiddling with the fact that we couldn't remember exactly what was what, and we started calling these P's. These P's are bosonic. We started to call these bosonic. because there is a kind of boson-fermion correspondence, and these are fermionic. And then came the electronic Macdonald polynomials. And it's actually really quite helpful for, I encourage everybody at coffee to talk about them in terms of boson, because it makes it much easier to keep them straight in your head. Historically, the P's were called symmetric Macdonald polynomials. The E's were called non-symmetric Macdonald polynomials. And I think the A's were just left. I don't know what happened to the A's. Okay, but you really need, as you can see, for our two fundamental formulas, we have the bideterminantal formula, we have the generating function formula. For these two formulas, we need all three parts: bosonic, fermionic, and electronic. So I think that the fact that the Macdonald theory could put all of that together is really remarkable. Okay, so I think I'm doing well on time. So let me go a little bit on the details of this first formula, which is the generating function formula. So it's exactly the same as before. This B lambda is the set of semi-standard Young tableau. So it's still trying to be a generating function. The only thing is that these weights, phi t, qt, before they were all 1. So now the weights have gotten changed. So that's what we have to tell you. Okay, so what are the weights? So this is a product over the boxes in lambda. So this is boxes in lambda. And I think I have a slide here. You see, here's a box. This is a box. So this is a product over the boxes. Well, that's not too bad. As combinatorists, we can take a product over the boxes. We feel fine with that. Okay, so now what is this HT? This is a hook, a QT hook number, hook function, let's call it. Function. And it's a QT thing. It depends on both Q and T. So how do you make that? Well, this is how you make this. So I hope you can see this formula. So it's a product. So this section is called the arm, and this section is called the leg. Right? That's the arm and the leg. And so we're going to take a product over I, which appear in the arm. But the condition is that they do not appear in the leg. So 5 is an example here. 5 appears in the arm, but it does not appear in the leg. Okay, now for each of those, we're going to take a quotient of 2 hook polynomials. And what we do is we look at the part which is less than the I that you're looking at. So this is a part which is less than 5. And in the denominator, we'll look at the part which is less than or equal to 5. All right? Okay, so that's not so bad. Oh, what happened here? Where did my... Oh, it's going the wrong way. It's going the wrong way. Where did my tableau go? Oh, there it is. Okay, good. I thought it disappeared. I don't know what I did. So these polynomials these rational functions that we appear here, this is what it looks like. So you look down your arm, and you look at all of the ones that are less than 5. And that's this arm less than 5. And you look down your leg, and you look all the ones that are less than 5, and that's this leg. And similarly here, and you have the same numbers in the numerator and the denominator. The only difference is whether this box that we were looking at here gets a Q or a T. So in the numerator, it gets a T, and in the denominator, it gets a Q. So you may remember, if you've read chapter 1 of Macdonald, that the hook length is the arm plus the leg plus 1. And that plus 1 is changing from Q to T. So in fact, this is what the dials do, is they just change that plus 1. All right, so anyway, the point is that it's a perfectly friendly statistic. And it's also perfectly easy to see that when you specialize T and Q to 0, it gets 1. So we should never be scared of Macdonald polynomials. They're perfectly good. Okay, so now we can go to the bideterminantal formula. And so I want to tell you again, what are these actions? What are this Hecke action and what is this electronic Macdonald polynomials? So the Hecke action is you take this is the old symmetric group action. All it does is switch xi and xi plus 1. So that's the old symmetric group action. Now, what do you do? So there's a factor of t to the minus t to the half. So really, I should have factored out a t to the half from this term too. Pretend we factored out t to the half. Then this is a minus 1, and this is a plus 1. Minus 1 and a plus 1. So the minus 1 is trying to cancel the plus 1 if you factor out it. Okay. Except that I've multiplied by this crazy factor. And this crazy factor is, Macdonald explained to us that this is called a C function. This is an analog of Harish-Chandra's C function. And if you just multiply by this crazy factor, and then use this modified BGG operator, if you think in terms of Schubert calculus, this gives this Hecke action. So in particular, again, it's not such a complicated deformation of just the switch. And you replace that with the ordinary SIs, and that gives you this fermionic Macdonald polynomial. Fermionic means alternating determinant. So in fact, this formula is also quite easy to state, and it makes complete sense that it's an analog of one determinant divided by another one. But as I said, the proof, oh, I forgot to say what our electronic Macdonald polynomials. So electronic Macdonald polynomials are made the same way Schubert polynomials are. You start with a simple one, and then you have a machine. So all we've done here is add one box. So this adds one box and rotates the thing. And this adds this factor and rotates the variables. And this one permutes two parts of your composition and does this crazy operation, which comes from Schubert calculus. And that builds the electronic Macdonald polynomial. So again, if you've ever studied Schubert polynomials, then electronic Macdonald polynomials feel very similar. All right. So there's the point. This is the main point, is that Macdonald polynomial theory is completely an analog of the classical Schur function theory, and the definitions are not so scary. So that's I think, an amazing. And the big question, which I would like, is how do you give a. Really, I would like a combinatorial proof, but I actually know 4 or 5 different proofs, in the Schur function case. So in the Schur function case, I know this, and my favorite one is to use crystals. But I do not know how to do QT analog of crystals in any way to get these formulas. So I think this is a big question that we should all think about. Yeah. Yeah. That is not a typo. So Sarah is pointing to this. Okay. So Sarah's pointing to this QT here, Q and QT. And notice that when Q and T are 0, Q times T is 0. So this is okay. But this is actually really a subtlety, and this is in fact what makes the Cherednik recursion work. So they're just equal as polynomials. Take P lambda QT, and everywhere you see a T, replace it by QT. That gives you a new polynomial. And that polynomial is what's on the left-hand side here. Is yeah, so you can take these weights and every place replace t by qt, and you've got a bunch of objects on the left-hand side with weights. And then on the right-hand side, you of course have to deal with the same problems you have to deal with in Schur functions. Is how do you deal with this quotient? And usually we multiply both sides by the Vandermonde, which is now a new T Vandermonde. It's a generalized Vandermonde, which is a very beautiful object. I could go on and on. Yeah, I could go on and on. So we'll stop at 8. What did you say? All right. So this is the next question. Of course, in my business, in fact, it was my first PhD, the research problem. The first thing that Adriano Garcia gave to us was, can you do type B? They had done type A, do type B. But here, Macdonald has something very interesting, which I was not told until many years later. So he has something very interesting to say. Which type B? I said, well, type B. So in 1972, Macdonald pointed out that there are 9 different type Bs. Okay? And this is actually, it's amazing when you start to think about type Bs and after you learn this result and you try to think which of the 9 it is, it becomes really quite interesting. So we've been in several talks, we've been seeing this cyclic shift. But when you try to do the cyclic shift in type B, you will have to deal with these 9 cases. Somehow the analog of this cyclic shift is what causes the differences. All right, so there are 9 different type Bs. And this is the picture of them. So I think it's a little bit small. So one of the reasons I wanted to use the iPad is so that I could hopefully do this trick. All right. So this is a poset. And this is a poset of affine root systems of classical type. So first of all, that's an amazing statement, is that, in fact, we should think of all of the affine root systems as one inside of another one, inside of another one, and so on, for classical types, so not exceptional types. And then this poset has a unique minimal element. I like to think of this minimal element down here as dn. Yeah, it's not so happy with me, this. Oh, I see what it did. So it jumped to. Let's see if we can find. There we go. So I like to think of this minimal element down here as type D. And there's a unique maximal element that's type C. I don't know why it's. And GLN is really somehow below type D. So GLN, this special case, is type D. Okay, but and each of them has a Dinkin diagram, and each of them has been discovered by several people. So the left notation, so if I'm looking at one of these cases, the left notation is the notation of Victor Katz. Victor Katz discovered these in connection with Katz-Moody Lie algebras. The right notation is the notation of Brouatitz. Brouatitz discovered these in connection with reductive groups over local fields. They were classifying p-adic groups. And the middle notation is Macdonald. So you know which notation I use. Okay. So the top one, so Victor Katz actually didn't do the non-reduced root systems, but Macdonald and Brouatitz did. And the top one is called CN check CN, this one here. Let's see if we can switch pans. And CN check CN is at the top. And if you do the Macdonald polynomials for CN check CN, they have 6 parameters altogether. 5 parameters for 5 orbits of roots, 5 conjugacy classes of simple reflections under the root system, and then an extra parameter Q. And the miracle is that if you do CN check CN, then all of the other cases are special cases. And you can see that in this diagram. What happened in going from here to here? Well, this parameter, you got changed to 1. So this diagram contains all the Macdonald polynomials for all the classical types at once, including GLN, because there's a way to take the top homogeneous component and get the GLN case. So everything is in this one picture, which I find is completely amazing. So that's the question. Can you do type B? Which type B? That's the one. Okay, so next I want to go back to this. So now the next thing I want to talk about in Macdonald's oeuvre is cohomology. So this is an older result of Macdonald. It was in 1962. So Macdonald did not get a PhD. No PhD needed, right? So, and he did math tripos at Cambridge at Trinity College. And after that, his father was insistent. His father had been through 2 wars and a depression, and he was insistent that you should get a secure job. And in those days, a secure job, at least in Macdonald's father's idea, was a government job. So Macdonald got a government job. And he told me, I stuck it for 5 years. He really didn't like that job, but he did it for 5 years. And then he moved to a temporary position. I don't know if any of you have ever been in a temporary position. But Macdonald did it too, just like me and just like everybody. And in this temporary position, apparently he had really quite a lot of teaching. It was not the nicest temporary position. And in this time, he did an amazing thing so that 4 years later, or 5, depending on how you count, he wrote this incredible paper about cohomology. So this is a story of cohomology of a symmetric product of a curve. So I've drawn a picture here of a curve. Let's see, yeah. This is a curve. So what is a curve? A curve is a one-dimensional manifold. This is a one-dimensional complex. We're working over complex numbers. So this is the complex plane, right? Everything is complex. And it makes sense that it should be complex. And actually, as you know, if you stand on a one-dimensional manifold, it looks flat. So, right? But of course, as you know, all manifolds are compact, because otherwise I couldn't go to Australia and come to Germany. Right? So you look at one-dimensional manifolds that are compact, and these are the curves. And curves can have holes in them, which is the genus, the number of holes. Okay, so that's a good story. And then, of course, everything has symmetries. I don't know if you can see the lines, but you can take this piece of paper and you can fold it along the symmetries, and you get a new space. And that's what this sigma n is. So you take your manifold, your sigma, your curve, and you just take mod the symmetries, and you get this new folded up space, which depending on your point of view is, well, and certainly in those days in 1962, it was a pretty scary space. And it still is a pretty scary space, actually. Because I don't know if you, well, just look at it, just stare at it like that and tell me how many pieces of paper are in between these two fingers, right? It's actually a pretty, and what is this sticky point here? It's pretty dangerous, right? So the same kind of things happen in these spaces. All right. So Macdonald said, I'm going to compute the cohomology of this curve. So what is cohomology? Cohomology is a machine. It's a machine that eats spaces and spits out graded rings. Right? That's all it is. It's just a machine, you know. I'm sure you've seen the people cut the trees, and they take the tree limbs and they put it in the machine, and it spits out. That's what cohomology is. So what does cohomology look like? That's what cohomology looks like. So it's actually, I mean, it's got big teeth, but it's actually cohomology is not scary. It's the spaces that are bad. The cohomology turns your horrible spaces into nice graded rings. So this really, okay, so Macdonald said, I'm going to compute the cohomology of a symmetric product of a curve. And, well, how do you do that? Well, a graded ring, so the question, if you want to compute the cohomology of something, you have to compute a graded ring. And now I ask my algebra students, how do you write down a graded ring? Well, a little bit of experience, how do you write down a Hecke algebra? A little bit of experience tells you write down generators and you write down relations. There's more or less no other way to write down a ring. Right? And graded means you better tell me the degrees of these generators. Hopefully they're homogeneous. Okay, so that's what he had to do. And it's quite easy to determine the number of generators. So there are, if your space has G holes, then there are 2G plus 1 generators in this cohomology ring. And I don't know if you've ever played with presentations, but that's beautiful. You don't have to read it. Just look at it. I mean, right?
CJ equals negative CJ.
Yeah, there's a typo there. Yes, thank you, Frank. That's a good. You're a good CJ. So it's an exterior algebra in two different sets of it's two different exterior algebras patched together. All right, but it's so. I don't know if you've ever read Macdonald, but that's Macdonald already, right after his non-PhD, writing in the same beautiful, elegant fashion. And so if you want to know this ring, you just get out and start computing, right? Whatever. So I find that really striking. So yeah, okay, so we computed the cohomology of a symmetric product of curves, but does it have any applications? And the answer is yes. There was this thing called the Weil conjectures. Weil wrote a paper in 1949 with these conjectures. And the whole world of algebraic geometry started trying to prove these conjectures from 1949. It was a huge machine. Grothendieck started a huge machine building étale cohomology, L-adic cohomology, the whole bunch of tools. And they were proved slowly until the final one of the Weil conjectures was proved by Deligne in '74. We're talking 1962 here. So what are the Weil conjectures about? The Weil conjectures are about the zeta function of an algebraic variety. So I want you to think of an algebraic variety. X squared plus y squared equals 1. I don't know if you've seen that one before, right? Okay, but that's an equation, and you want to know what are the solutions. But you want to know what are the solutions over fq to the n. So take x squared plus y squared equal 1, you can do it right now, and tell me what are the solutions over f27. How many are there? 28? Okay, good. It is P1, yes, thank you. Yeah, ask Frank. I didn't actually. But ask your undergraduate class if they'll come up with 28. It takes a little bit of extra thinking.
Do your undergraduates know finite fields?
But yeah, we try to teach them, yeah. Anyway, you got the picture because Frank can tell you the number right away. And we are combinatorics. So we put this in a generating function. So F5, F25, F125, tell me the number of points in a circle for all of these, and put them in a generating function. And that's what it is. That's the zeta function. So in fact, the zeta function is a combinatorial problem. I give you, okay. So now Macdonald says, let's assume that we know the zeta function for sigma. Remember what we did is we took a symmetric product of a curve. So we took C, C2, C3, C4, and then we took symmetries. So sigma, sigma squared, sigma cubed, sigma to the fourth, and then we take symmetries. So we start with sigma, and we assume, okay, let's say we know the zeta function of sigma. Then Macdonald builds two things. He builds this phi k of t. So it uses the roots of the zeta function of sigma. You take just the curve and you look at the roots of the numerator, and you use those roots to make this phi k. And for those of you who like plethistic notation, it's a beautiful little exercise to do this plethism with an elementary symmetric function. Okay. So those are the phi's. And then these are the f's. These f's are phi k minus 2, phi k minus 4, so on. So that's a pretty easy construction. Build the phi's, build the f's. Theorem. This is the zeta function of the symmetric product. This is a corollary of that cohomology computation. So it was an amazing, compute the cohomology, bam. Here's the zeta function of the symmetric product. And that proved, so then just by looking at that proved the Weil conjectures for the symmetric products of a curve. There are three Weil conjectures. One is that the structure of the zeta function in terms of Betti numbers, which is what that first one is. The second one is called the Riemann hypothesis, which gives some region where the roots lie. And the third one is the functional equation. And these are just bam, bam, bam corollaries in Macdonald's paper of the cohomology computation. All right, so that was Weil conjectures. So now I'll tell, I am going a little bit slower, but I hope you'll forgive me and just going slow and telling the stories, because I want to tell this story. So I don't go to England very often. I tend to come to Europe and visit. My friends are mostly Switzerland, Germany, France. But I do go to England when I can. And whenever I would go to England, I would always try to stop and see Ian Macdonald and his wife, Greta. They were very good friends. Greta was a very good friend of my wife, and would, in those days, we didn't have organized childcare at conferences, but Greta was the organized childcare at conferences, took care of my daughter many times at FPSAC and other times. And so I went to the last, after Greta died in 2019, I happened to be in England twice, and both times I saw Ian, even though Greta wasn't there. And this last time I arrived, and he immediately told me, well, I haven't thought about mathematics in 15 years. He showed me the newspapers. I said, see the Sudoku puzzles. And he was trying to produce evidence to convince me that he hadn't been thinking about mathematics. So we chatted, we would chat about friends, about Adriano Garcia, and about mathematics and about history, because of course he was just full of history that I didn't know about the mathematical community in the past and so on. So I learned a lot. And then I invited him and his sister across the road to the pub for dinner, because just as a gesture. And we went together, and we had fish and chips and beer. That was what he liked. And we were talking with his sister, and at some point, she said, oh, but Ian, weren't you working on some circles and triangles or something? And he was trying to pretend that he hadn't been working on math, but apparently he had. So then he told me, yeah, I was thinking about something. Okay, I didn't push it. We went back to his house, and we were chatting again. And at some point, he lifted himself out of his chair, and he walked across to the table there, and he picked up some papers, and he handed it to me. He gifted it to me, the manuscript. And he explained that this manuscript was a supplementary chapter to a book that he had written right after high school, when he was 18 years old, before his military service. And the book was about circles and triangles and Euclidean geometry, mostly in the plane. And he had lost the manuscript apparently, but still there was this supplementary chapter. And then later his son sent me actually the scans of the original handwritten. What he gave to me was a LaTeX document, but later his son sent me the scans. And this is a scan of the first page of this supplementary chapter, which is called the 4-line, 5-line, and N-line. And the story of this is very beautiful. You take two lines, generic lines in space, and I think you'll be convinced that they intersect right here in a unique point. Right? Now, that point is, we'll call it the Clifford point of the 2-line. Now take 3 lines generically, and each of the 2 lines intersect in a point, and those 3 points determine a circle, a unique circle. All right. That circle is the Clifford circle of the 3-line. Okay, now you take 4 lines, and each 3 of those 4 lines determine a circle. So each 3 determine a circle, and you have those 4 circles, and now you have a non-trivial thing appears, and that is that these 4 circles meet in a unique point. That's magical, because you draw some 4 circles, you don't expect that to happen. Okay, that unique point is called the Clifford point of the 4-line. Historically, it was called the Wallace point. Macdonald called it the Wallace point. Take 5 lines. Each of those 5 lines determines a Clifford. Each 4 of those 5 lines determines a Clifford point. Now you take these 5 Clifford points, and miraculously, they lie on a circle. A circle, right. Not just any kind. It's amazing. And this is what this manuscript is about. It's about 45 pages, typed. It's beautiful. It's not beautifully written. I mean, this high school student should have taken lessons from Ian Macdonald. You know, he needed some better exposition, but it is quite amazing to see the thoroughness of this 18-year-old and the way that he does mathematics. So, for example, this is a picture from those scans. So you can see how did this 18-year-old work when he was analyzing such things. He obviously making such a picture took forever. Then he made a general formulation. So he said, how do I write down a line? Well, I can write down a line by choosing 2 points in the complex plane, and the line is the points that are equidistant between 0 and yi. So if I want to write down n lines, I just choose n generic points in the complex plane that are non-zero, and then I take the lines that are equidistant from each of those, and that's an n line. That's how I should do it. So that's the data, and you can write down a specific formula for the line in the complex plane from that data. All right. So then Macdonald defines, this is 18-year-old Macdonald. He defines this object where these GNs in the denominator are these, this kind of elementary symmetric function with 1 variable removed. And I think something is wrong with this slide because the p's are not defined, but it doesn't matter. We don't need to go till 8. The point was that he defined these c's, and these c's don't have such a horrible formula, and it's kind of a Newton identity for elementary and symmetric and power sum symmetric functions. And then he writes down explicitly the formula for the Clifford point. Explicitly, right? And we actually found a paper from 2005 saying that this had never been done, right? So I guess it had never been published, but Macdonald's manuscript had never been published, but certainly Macdonald wrote down the Clifford point, and he wrote down the Clifford circle for the other case. So you get opposite of circle. So then I was shocked. I read this. I had some undergraduates help me read this manuscript. And I was shocked to realize that Macdonald started with this question when he was a high school student. Then he went through university, he went through military service, and then he got a government job. And then he couldn't take it, so he got a teaching job. And he had to start doing mathematics. So he started again with intersection theory. And his first paper is about Schubert conditions, Schubert calculus. And he reproves de Jonquier's theorem in a beautiful way, which is a theorem from the time of Schubert. And he uses Giambelli identities and Pieri identities. He was really in Schubert calculus. And his third paper was the proof of the Weil conjectures for symmetric products. And so I looked at the proof of the Weil conjectures paper, and I looked at the introduction, and he says, the point of this paper is to do the computations from my intersection theory paper in a simpler way. So that's how Macdonald got started in mathematics. He started in high school intersecting lines and circles. And then he moved on to Schubert conditions and was doing Schubert calculus. And then he proved the Weil conjectures for symmetric products and computed the cohomology of a symmetric product of curves, right? It's just marvelous. Okay, so Macdonald the influencer. So there wasn't social media, and I do think that that's something that Macdonald never did, it wasn't social media. But he was an incredible influencer. So this is a paper by Molik and Yun, who are big-time algebraic geometers, geometric representation theorists, and they are exactly trying to generalize, I can't blow this one up, I don't have generalize Macdonald's cohomology computation of a symmetric product of curves. So this is going on and is very much alive and well, particularly with the way that we study moduli spaces of curves these days. And in fact, if you talk to an algebraic geometer or a topologist, they've never heard of a Schur function. This is what Macdonald did. Right? It's incredible. All right. Victor Katz, if you read this, he says, at about the same time, Macdonald in 1972 obtained his remarkable identities, generalizing the Weil denominator to affine root systems. And he goes on. And this was the connection to Kac-Moody-Lie algebras. Great, a huge influence at the time. And if you read Dyson, I didn't include Dyson, but that's another. This one blew my mind. So this is Deligne and Lustig, who at least in my world are important figures. And this says, in 1968, Macdonald conjectured, based on chapter 4 of Macdonald's book, which wasn't out yet, general conjectures for all reductive finite Chevalley groups about how the representations are labeled. And Deligne and Lustig, not quite 10 years later, 8 years later, proved them by introducing what's now called Deligne-Lustig induction. All right, so he was an influencer. This one is one of my favorites just because this manuscript, which is called Spherical Functions on a Group of P-adic Type, has been one of my favorites. This is a paper of, well, a little book of Castleman. Castleman was a very important figure in P-adic groups, still is an important figure in P-adic groups. And Macdonald wrote a beautiful book called Spherical Functions on P-adic Groups, which had changed my life. Amri is saying yes. It completely changed my life. That was how I got into Hall-Littlewood polynomials and alcove walks and things like that. Macdonald as a translator. So I don't know if you knew this, but if you read Bourbaki in English, you read Macdonald. So I'm absolutely sure that he did the two topology ones, and I'm pretty sure he did all the others, but there seems to be no record of exactly which ones he did. So it's possible he didn't quite do them all that I've listed here, but I think he did. If you count up the pages of these, that's 2,500 pages of Bourbaki. I don't know if you ever tried to copy Bourbaki, all of those volumes, but you know, it's an amazing contribution to our community. And that's not all. Dieudonné. So it's, I suppose, not as popular as it was when I was a graduate student, but this used to be the Bible in analysis, Dieudonné, Treatise in Analysis, a whole bunch of volumes. They were translated by Macdonald into English. And again, some 2,500 pages of stuff. For my students, so this is what happens, right? Every once in a while, actually not infrequently, a student comes into my office and says, I really would like to learn Lie groups. Do you have a reference that you can recommend? And I think about it for a while. And then I say, how about the notes of Macdonald, right? A student comes into my office and says, I'd like to learn algebraic groups. Do you have a reference you can recommend? How about the notes of Macdonald? Student comes in and says, these Coxer groups are really cool. I'd like to learn reflection groups. Do you have a reference you can recommend? How about the notes of Macdonald? Or student comes in, this book, Hartshorn, is killing me. I really want to learn algebraic geometry. Do you have a reference you can recommend? How about the notes of Macdonald? Or Kac-Moody-Lie algebras. Oh, Haar measure, spherical functions, harmonic analysis. How about the notes of Macdonald? Kac-Moody-Lie algebras. How about the notes of Macdonald? So pretty much we don't, there's just so much information there. A lot of it is unpublished, unfortunately. Maybe we can do something about that, but it's available if you start asking around. Particularly if you ask me, I seem to have copies of things, and I'm happy to give them to you. Flag varieties and Schubert varieties. In this conference, everybody wants to learn that. How do you do it? Look at the notes of Macdonald. Books. So the last time I saw Macdonald, he told me one thing. He said, if you see a gap in the literature, write a book to fill it. I didn't know if I should take that as advice or what. Macdonald was a pretty soft-spoken and didn't speak a lot of sentences normally. He didn't talk a lot like me, but he would say one thing and then let you think about it for 5 years or something. So I looked up his books. So these are a few books. Atiyah and Macdonald, The Introduction to Commutative Algebra. No, don't know if you heard of that one, but we were forced to read it when I was a kid. Spherical Functions on a Group of P-adic Type. Symmetric Functions and Hall Polynomials, 1979. So I consider that a separate book, because a few of us old people, we actually have this slim volume of first edition. Kac-Moody-Lie algebras, which unfortunately was unpublished. Hypergeometric functions, which is on the archive. It's not finished. It needs to be finished up. Reflection groups, which is in pretty good shape, but it's unpublished. And that's not all. Schubert polynomials, which is published by Lassim, and I've heard that it's going to be much more easily available quite soon, hopefully. Oh, I have. You can get it also from my webpage, but I think there will be an official distribution of it through Lassim soon. I count this as a separate book. This is second edition. Because if you put the two books next to each other, it's clearly a second book, right? This one is just hugely different. So that's yet another book he wrote. Linear algebraic groups. He has a beautiful little book on linear algebraic groups. Affine Hecke algebras and orthogonal polynomials. This is the one about Macdonald polynomials in general type. And that was the first book, was the algebraic geometry book, Introduction to Schemes. Again, it's typical Macdonald. It's a thin little volume, but I still swear by it. Everything that I know about algebraic geometry, I learned from this one. All right, so there was one theorem that I learned, again. Macdonald had told it to me, but I learned again preparing this talk. And I was looking at Macdonald's trajectory. I can see the proof of this theorem, and that is, one starts out in life trying to do something else, and one winds up doing combinatorics. And that's why we're here. Let me finish that.
Okay, thank you very much for the amazing story of Macdonald. Are there questions?
Since you skipped over, you talked about his first paper, his third paper. What about his second paper?
So it's not completely clear what order things came in because he started working pretty madly after the first. So there's a little paper on Jordan algebras, which means that he was sort of in touch with that world, which was a big world at the time because of Adrian Albert. He doesn't seem to have returned to Jordan algebras. And then there's another combinatorial paper about the Poincaré polynomial of the symmetric product of the curve. Those were obviously connected to his cohomology computation. And then it's clear he started to get some attention, and he starts to do other things. One is related to plane partitions, and it's pretty hard to pin him down and to know. The leaps between works are pretty huge. And so to try to figure out what he was thinking at any given year is pretty tough. But yeah.
Are there more questions? Okay, then let's thank Arun about the beautiful talk.